As we develop our familiarity with the first law of thermodynamics, it's very useful to understand exactly how energy does get exchanged between systems and surroundings, and how we can understand concepts like heat and work. In this video, I want to talk a little bit about what is heat and define a property of matter known as heat capacity that'll help us to calculate the amount of heat that is exchanged during the course of some kind of thermodynamic process. So we'll start by considering a thought experiment, if you will, or at least a hypothetical experiment. I'm going to imagine that I have two objects that I'm going to bring together, and at their borderline they have some kind of thermal conduct. They can conduct thermal energy across this contact between themselves, and they're at two different temperatures, T1 and T2. Now, we're also going to isolate this system from the rest of the universe by putting an insulating barrier around it. Now, we'll assume that the T2 is greater than T1, so we have a hot side and we have a cold side in this process. And our intuition tells us that generally speaking, we're going to have heat that flows from the hot side to the cold side, or in other words, there is going to be some kind of energy exchange between these two parts, these two pieces, that goes in this direction. All right, so we'll expect to see the side with T1 to heat up a little bit and the side with T2 to cool down a little bit until they reach the same temperature, and that will define something we call thermal equilibrium. So the key question that we have for this lesson is, what would be that final temperature? So if we call it T sub F, how can we calculate T sub F? Now, the first and perhaps most logical thing to presume would be that the amount of temperature change will be the same on both sides. So in other words, this difference will be the same. The amount of temperature lost on side 2 will be equal to the amount of temperature gained on side 1. Now, if we presume this, then what we'll get is that T sub F should just be an average of T1 and T2. And, it is a reasonable assumption. It is even true sometimes. However, we find that it is only true if we have the same material on both sides of this and they are at the same mass. Okay, so that's pretty restrictive. If we had different materials there, or if we had different masses, this would not be true. So another way we might construct this is to say, well, what if we weight this with the masses of the two pieces? Would that fix this problem? In other words, will we now have an equality here and a way to calculate T sub F if we multiply both sides by the masses of those pieces? And it turns out that this again is true sometimes, but it is only true if it is the same material on both sides. So we haven't quite cracked the code for how energy is exchanged here, how heat is exchanged to equalize these two temperatures. So at this point, what a lot of scientists would do would be, maybe add an adjustable parameter or two. Well, in this case, we could stick adjustable parameters in here and make sure that this fits the available data. And in fact, I will tell you that given that we have two adjustable parameters here and only one unknown, namely the final temperature, we'll be able to fit this pretty well. And in fact, we'll find that an equation like this can always be used to fit the known data. But the real test of this is, will this work for any combination of masses, or will it work for any combination of initial temperatures? And it turns out that in this particular case, if you try this for several different values of T1 and T2, or for several different masses M1 and M2, you do get the same values for C1 and C2. All right, so there is something about this that does work. There is something about this that is intrinsic to the materials that are used in this experiment that will make this true. And in fact, what we can do is we can attribute C1 and C2 to intensive properties of that material. In other words, they are specific to that material. And in fact, if we were to construct this experiment using different combinations of materials, so not just two materials, but let's say we had a whole bunch of different materials, and we ran this experiment with different temperatures and different masses of all these different materials, we would always get the same values of C, little c, for a given material every time. Okay, so there is something that is very important about this. Well, in fact, we have a name for this, and we call it the specific heat capacity of the material. So C1 and C2 represent the specific heat capacities of material 1 and material 2. Moreover, if this is an intensive property, when we multiply it by the mass, that is how we scale it up to be relevant for the whole object. So mass times the specific heat capacity gives us a heat capacity for the entire object. So in fact, we can now associate those products with the heat capacity of the object. And now if I took that same object and put it in an experiment for thermal equilibrium with another object, that heat capacity would be the number that I would need in order to determine the final temperature. All right, well, this is an interesting foray into heat exchange, and we learned something about solid materials, but what if we have a gas? And I want you to imagine now that instead of two solid objects, I've got two objects that have good thermal contact, but they contain gases at different temperatures. Now, since these objects are confined, this represents a constant volume system. So we're going to be caring about the thermodynamics of a constant volume sort of process. Well, I'll remind you that when we look at the differential change in internal energy, that we can express that as an incremental change in heat and an incremental change in work, which we can then express as dq minus pdv. Remember that the minus sign is there because when a gas expands, when a system expands, it is doing work on its surroundings and it is losing the energy. When the gas compresses, so dV would be negative, then it is adding energy to the system. So that negative sign is very important here. Now, it's all academic in this particular case because we have constant volume, so that means that this thing is going to be zero, so the whole thing is just equal to the incremental change in heat. I'm going to add a subscript V to indicate that this is for a constant volume process, and that V is something that tells us about the path for the change in the process. All right, so where can we take this further? Well, let's now make a definition for this quantity that we've called the heat capacity. I'm now going to attach that subscript V to this as well because this is relevant for a constant volume process. And in essence, what we're saying is that the heat capacity is equivalent to the incremental change in heat divided by the differential change in temperature. So in other words, it's that ratio of incremental changes that gives the heat capacity its definition. Now, since Q sub V is, by the equation we've just written down below, equivalent to the internal energy differential, we can actually write this out this way in terms of a state function. So now this C sub V is equal to the differential of U, the internal energy, with respect to temperature, but we have to specify that constant volume. And so I want to emphasize again that this is defining the path of change, and so that is in effect making the heat exchange be a state function because we have defined the path. All right, once we get to this point, we actually get to a very important result that you'll need to know to solve some problems. And that is that whenever we have a temperature change going on in a process, we can relate that to the internal energy via this constant volume heat capacity. So because U is a state function, delta U is going to be the integral of du from state 1 to state 2. But when we have this for a temperature change, we can make those the state 1, state 2 quantified by the temperatures, and it's just the heat capacity, which in general is a function of the temperature. It's the integral of that from T1 to T2. Now, I will point out that if the temperature difference is not that great, a lot of heat capacities don't change very drastically with temperature, so we can treat them as being nearly constant. And when that's the case, this integral actually simplifies to being just that constant value of the heat capacity times the change in temperature. So I hope this has made some sense and will help you understand why you are defining things the way we are and why we're using some of these expressions to solve some of the problems that you're given.